Now let's dive into how to solve these recurrence relations. And we will start with the case of linear, homogeneous, constant coefficients, and degree 2. So the examples in the beginning that we saw, both are of this form. They were an equals an minus 1 plus an minus 2. You can see that this is linear because these aren't getting multiplied. It is homogeneous because there is no extra term. The coefficients are both 1, so they are constants. And it's degree 2 because the smallest term appearing is n minus 2. And the other one was an equals an minus 1 plus 2an minus 2. So almost the same, except the coefficient on this term has changed. And in general, a recurrence that satisfies all these conditions will always have the form an equals constant times an minus 1 plus another constant times an minus 2. These are, let's say, real numbers. So there are two key ideas for how we're going to find the solutions to these recurrences. The first key idea is that a sub n equals r to the n. So we have a solution of this form where r, so r has to be something very special, of course. It's not going to be just anything. A sub n equals r to the n is a solution. If r is a solution of the corresponding characteristic equation which is gotten by taking the recurrence relation and replacing a sub n with r to the n. So essentially making this swap. And then we reduce down the extra powers of r. So in this case, we will get r squared minus c1r minus c2 equals 0. I'm going to put it all on one side also. But you can see that this is coming directly from the recurrence relation. First of all, I'm just shifting these to the other side. And then I'm just replacing this becomes a 1, this becomes an r, and this becomes an r squared. So just taking powers of r from the lowest being 0th power to the highest being whatever it has to be. Let me undo all that mess that I made of that equation. So this is what the characteristic equation is. And we're saying that the roots of this characteristic equation, which we usually call r, they give us solutions of this form. A sub n equals r to the n. And having explained what this means, maybe let's go a little bit further and check it really quickly. But it basically comes down to the fact that we're just taking this and substituting this substitution. So observe, if r satisfies the characteristic equation, which I will immediately start abbreviating because it is very long, then r squared equals c1r plus c2, just by shifting these terms over to the other side. And if we multiply by some power of r, we get r to the n equals c1 r to the n minus 1 plus c2 r to the n minus 2. That's just taking this equation and multiplying by r to the n minus 2. And you can see this shows an equals r to the n is a solution, because this equation is exactly this equation with that solution plugged in. So it shows that it works. So the first key idea is to form the characteristic equation and find the roots and find these forms of solutions. That is the first key idea. The second key idea is that we can find all solutions by taking linear combinations of those. So if a sub n equals s sub n and a n equals t sub n are solutions, so what's going on here is that if we just have a recurrence relation and we don't set any initial conditions, then in general we'll have many different solutions corresponding to the many different initial conditions that we could set. So if we have two solutions to this recurrence relation, then any linear combination let's call it a n equals x times Sn plus y times Tn. X and y are real numbers. Any linear combination is again a solution. And let's check this very quickly. So x times Sn plus y times Tn. Since Sn and Tn are solutions, we can go ahead and use the recurrence relation on both of these terms. And when we do that, we get x times c1 Sn minus 1 plus c2 Sn minus 2 plus y times c1 Tn minus 1 plus c2 Tn minus 2 and then rearranging this a little bit, basically when we distribute the x and distribute the y, we will get 4 different terms. And then we can collect these two terms and factor out the common c1, and then these two terms and factor out the common c2. So I'm going to do all those moves at the same time. And what we get is c1 x times Sn minus 1 plus y Tn minus 1 plus c2 x Sn minus 2 plus y Tn minus 2. And this shows that it is a solution because this is a sub n, this is a sub n minus 1, and this is a sub n minus 2. So this equality shows that it is a solution to the recurrence relation. So essentially, these are our two ways of building solutions, are to use the roots of the characteristic equation and then take linear combinations. And it is a fact if the characteristic equation has distinct roots, so in this case, it's a polynomial of degree 2, it can either have two distinct roots or it can have a double root. So in the case that it has distinct roots, R1 and R2, the general solution is a sub n equals x times r1 to the n plus y times r2 to the n for x and y real numbers. Meaning that every solution to the recurrence relation is of this form for some constants x and y. So you get all of the solutions basically by applying these two fundamental rules. And I might point this out a few times, but if you have any familiarity with differential equations, you will notice that our techniques and formulas for solving recurrences are extremely similar to the techniques for solving certain kinds of differential equations. So if you have seen that, you will be able to notice that difference. If you haven't, then if you ever take differential equations, well, you've already seen it. So let's do some examples. For example, well, let's do the ones we gave in the start. Fibonacci numbers. So these are defined by fn equals fn minus 1 plus fn minus 2, f0 equals 0, f1 equals 1. So the characteristic equation, what is this thing? It is r squared minus r minus 1. Because remember, we need to get them all on the same side, so we get the minus signs in there. And the coefficients are just 1. So the characteristic equation is r squared minus r minus 1. And roots are r1. Let's see. Let's use the quadratic formula. I am ashamed to say that when I was preparing this lecture, I totally forgot the quadratic formula, which is terrible. It's such a useful thing. So let's remember the quadratic formula. It is minus b, which in this case is 1, plus or minus square root of b squared minus 4ac divided by 2a. So in this case, it's 1 plus or minus, oh, now see, I did it again. It's minus 4ac, and ac is negative 1, so the minuses cancel and it becomes plus 4. Quick question about handwriting, I believe. That is an equal sign. I hope that's what the question is referring to. So, right, these are our two roots of our characteristic equation. And let me go ahead and erase this and just simplify that down. It is 1 plus root 5 over 2 and 1 minus root 5 over 2. So we have two distinct roots, and we can apply the general rule that we just saw. So the general solution is an, well, let me say fn equals x times 1 plus root 5 over 2 to the n plus y 1 minus root 5 over 2 to the n. And now, for the Fibonacci numbers, we have initial conditions. So we don't want to stop at the general solution. We want to find the exact solution that will give us Fibonacci numbers. Once we give initial conditions, then there are not any longer many solutions. There is then only one solution. So use initial conditions to find x and y. And how do we do that? We basically just plug this formula in with n equals 0 and n equals 1, and that'll give us a system of equations that we can solve. So for n equals 0, we get, let's see, f0 is equal to 0. So we get 0 equals, and then plug in n equals 0 on this side. That just makes these terms both be 1, because anything to the 0 is 1. And we get 0 equals x plus y. And in the n equals 1 case, f of 1 equals 1. So we get 1 on this side, and then plug in 1 for n on this side. We get x times 1 plus root 5 over 2 plus y times 1 minus root 5 over 2. And this is our system of equations. So we can just solve this any old how that we know how to solve equations. Maybe for me, the most straightforward way is to do a good old substitution. So I'm going to solve this for y, which means y equals negative x. And then I'm going to substitute that into this equation to get this becomes x, and this becomes negative x. So I'm actually going to factor the x out, and it becomes x times 1 plus root 5 over 2 minus 1 minus root 5 over 2. And these things, so essentially the 1s will cancel, and the root 5s, this becomes a plus. So we just get root 5 over 2 plus root 5 over 2. That is root 5. So now we get x times root 5 equals 1. So x equals 1 over root 5, and y equals negative that. So this is our first example that we have gotten. We now have a closed formula for the Fibonacci numbers. Fn is equal to 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. And it might look a little bit complicated, but I want to just point out some of the nice things that this allows us to do. Oh, just run out of space. That's good time for it. So one thing that it allows us to do is much easier computation. Before, if you wanted to know the nth Fibonacci number, you had to compute all the Fibonacci numbers up to n, and that, takes a lot longer than just plugging into this formula. So for example, I brought an example of that. F25, you don't need to compute F1 and 2 and 3 and 4 and 5 up to 24. You just need to plug in 25 to this formula, and with the help of a computer, that tells you it is 75,025. No problem. And another thing that this allows us to do is get a better growth estimate. So I did not write down actually what we did before. Let me see if I can find it in my notes really quick. Because before, we gave some kind of growth estimate for these Fibonacci numbers. So here it is. What we said is that Fn is greater than 1 plus root 5 over 2 to the n minus 2. And this proved that they grow exponentially. But now we can actually say that Fn is almost, approximately equal to 1 over root 5, 1 plus root 5 over 2 to the n. And this is because this little guy is bigger than 1. So as n increases, it's going to grow exponentially. This term is smaller than 1. It's between 0 and 1. No, it might be between -1 and 0. But in any case, the absolute value is less than 1. So this term is going to shrink to 0 as n increases. And so this term, if you're thinking about growth, you can basically ignore it. And we see that Fn is basically governed by this. So this is a much, first of all, more precise estimate than this. And second of all, it's not just a lower bound, it's an actual asymptotic estimate that tells us it will get closer and closer to this as n gets bigger and bigger. How good. So let me erase this real fast. And I do want to do that other example that we went through in the beginning. So let's get another page and go ahead and do that. So what was the other one? This I think will be nice because the equation turns out to be a little bit less complicated. So another example, the other one was an equals an minus 1 plus 2an minus 2. And our initial conditions were a1 equals 1, a2 equals 3. So in this case, what is the characteristic equation? It is r squared minus r minus 2 now. We have 2 here. 0, and the roots of this well, I guess we could use the quadratic formula, or we could observe, if you can factor things by hand, that is always a fine idea. And I think we can factor this by hand into r minus 2 and r plus 1, because that will multiply to -2 and add to -1. Very good. So the roots are r equals 2 and r equals -1. We call them r1 and r2. And it has distinct roots. Very good. So we can use our general method to say the general solution is an equals x times 2 to the n plus y times -1 to the n. And when we plug in our initial conditions, so plugging in n equals 1, we get an is 1, and plugging in 1 on this side, we get 2x minus y. Plugging in n equals 2, we get 3 for an, for a2. And then plugging in 2 on this side, we get 4x plus y. And for the sake of time, let me not solve this out longhand. Let me just give you a quick peek at the solution. You will find that x equals 2/3 and y equals 1/3. And so our solution to this recurrence relation with these initial conditions, which is to say the number of tilings of a 2x(n) board with 1x2 and 2x2 pieces. This is the example that we got it from in the beginning. The number of tilings in this way, we don't just have a recurrence relation, we have an actual exact formula. It is 2/3 times 2 to the n plus 1/3 times -1 to the n. How nice.